First, I want to apologize to my Germanophone colleagues for my pronunciation of Hauptvermutung. Hauptvermutung. My apologies. So, I think a successful theory of quantum gravity ought to account for the success of the theories that it supplants. In part, for example, we might believe that the best success would involve explaining the range of validity of our previous theories. Philosophically, the role of intertheoretic reduction in this context has received little attention. Now, a lot of people have focused on emergence and reduction of properties. Here, the unit analysis is not properties or ontology, say spacetime, but the unit of analysis is rather a theory. Now, any approach will have to admit that because no program in quantum gravity has yet accomplished this reductive goal, any kind of analysis must be tentative. But I think nevertheless that it can be fruitful because it can suggest new ways and new approaches to intertheoretic reduction that are evinced by these programs in quantum gravity. So today I'm going to be focusing on causal set theory. One of the reasons why is that its structure in many ways is logically simple. So there's not as many bells and whistles that I have to deal with when I build things up. Additionally, the relationship of the theory with relativity has played a central role in its research program. In fact, the Hauptvermutung, or central conjecture of the theory, really actually concerns quite directly this relationship, the relationship of causal set theory with relativity. So here are some things I would like to argue about the Hauptvermutung. It describes the nature of causal set theory's hoped-for reduction to general relativity. I would also like to argue that yet it has no precise statement. There's still a number of undefined terms that need to be precisified. And I think that at this point a lot of philosophical work can be done fruitfully and in the spirit of, for example, John Ehrman's work on cosmic censorship. I would also like to argue that further attention to observables may help clarify it. That is, further attention to how observable quantities, or beatables, if you like, in a general relativistic space-time can well approximate similar kinds or corresponding kinds of observables or beatables in a causal set. Finally, I would like to argue that if a precise version of the Hauptvermutung were true, it would be an instance of a so-called non-Hegelian reduction. What I mean by that is that it would be an instance of an intertheoretic reduction that is not, in some general sense, a derivation of one theory by another. In this sense, if this is right, and if the Hauptvermutung were true, or some version of it were true, then its relationship, the reductive relationship between it and general relativity, would not be one of a derivation of general relativity from causal set theory. Now, unfortunately, arguing for all four of these things in less than a half an hour is beyond my pay grade. So I'm just going to focus on number 2 and number 3. And in particular, I'm mostly going to be focusing on number 2. I'm going to be mostly focusing on trying to get clear on what the conceptual and technical issues that need to be resolved are before the Hauptvermutung can be given a precise statement, and therefore before it can be actually proven or disproven. So, to set the stage, I'm going to motivate, in the standard way, causal set theory from results in the 1970s by David Malamud and others, and then I'm going to discuss causal set kinematics. And from there, we can kind of write down a heuristic Hauptvermutung that we often see in the causal set theory literature. So then I'm going to present 3 kinds of classes of problems. One has to do with, and I'll talk about what these mean later, how we understand the notion of a uniform embedding, in particular in a structure that is infinite. Another is how we're supposed to understand the concept of a coarse-graining in causal set theory. And finally, the notion of space-time similarity, what it means for different space-times to be similar to one another. All of these 3 play a role, in some sense or other, in the statement of the Hauptvermutung. In particular, I'm going to talk about 3 different approaches to understanding space-time similarity that have been at least proposed in the causal set literature. I think all of them still need quite a bit of exploration. And then finally, I'm going to have a short denouement on lessons for intertheoretic reduction. Okay, so to start off, here the setting is a relativistic spacetime. We have some points P and Q, and we can define the chronological future and the chronological past associated with the set. Here, the chronological future associated with P is just all the points that you can reach by a future-directed time-like curve emanating from P. And conversely, the causal past of this point Q, or the chronological past of the point Q, is going to be the set of points that we can reach by a past-directed time-like curve. And in general, if we have, say, a point that is in the chronological past of another point, we write it using this way-down relation here. So then we can define what it means for a space-time to be distinguishing. We say, in particular, that it's future distinguishing when for every pair of points in the underlying manifold, if their chronological futures are the same, this implies that the points are actually the same. And similarly, one can define a past distinguishing spacetime. So a distinguishing spacetime is just a spacetime that's both future and past distinguishing. These kinds of conditions are ensure that a spacetime doesn't contain any closed time-like curves, and in a certain technical sense, that it doesn't contain any almost closed time-like curves. So the theorem that influences causal set theory is this one. Two distinguishing spacetimes must be conformally isometric if there is a causal isomorphism between them. In other words, if we have some bijection between their underlying manifolds, if F and F inverse preserve the causal relation, the way-down relation, then there's a diffeomorphism between the underlying manifolds, such that when we pull back the spacetime metric from M prime to M, we get back up to a conformal factor the metric on the manifold M. It's a kind of remarkable result because it shows that you can reconstruct a distinguishing spacetime entirely up to a conformal factor by its causal relations alone. Now, the conformal factor is related to spacetime metric's volume element. So one can paraphrase this by saying that causal structure determines a spacetime up to volume, assuming it's distinguishing. So here's the idea behind causal set theory. If we can instead imagine spacetime being composed of discrete chunks, we could determine the volume structure as well if we assume that those discrete chunks all have some non-zero elementary volume. And then we could just count the number of discrete chunks to determine the volume. Hence, Raphael Sorkin's slogan in this context, order plus number is geometry. Okay, let's get a little bit more of the formal apparatus on the table. So a causal set is an ordered pair where we have some underlying point set and a relation on the point set that is reflexive, it's antisymmetric, it's transitive, and it's locally finite. So the first three components ensure that the relation is a partial order. The last encodes in a formal way what it means to say that that partial order is discrete. And that's it. So here's an example. We saw this before. Thanks, Chris, for the diagram. I'm going to limit attention to complete causal set histories, or you might call them block universe causal sets, which are in some respects classical objects. Now, the dynamics of the theory and the relationship of quantum fields on causal sets and so on is an important part of the research program, but I'm going to limit attention just to this aspect here. Okay, so here's the intuition behind the Hauptvermutung. If one samples enough points with their causal relations, right, from a space-time, one should be able to recover most of the geometry, right? Now, of course, if you think the causal set is more fundamental, then you don't want to be sampling points from an object of space-time you think is less fundamental. So we have to somewhat invert the relationship here. Rather, we have to say that if a causal set is such that it could have been sampled from a space-time, then that space-time is essentially unique. So let's try to make these a little bit more precise. So given a causal set and a relativistic space-time and an injection of the underlying point set of the causal set into the manifold of the space-time, we say that that injection is a faithful embedding with density rho just when two conditions are satisfied. One, the injection preserves causal relations. That's what makes it an embedding. And second, the image is mapped uniformly into M at density rho with respect to the volume measure arising from the space-time metric. So I have quotations around uniformly because that's going to be one of the main things I'm going to be talking about that needs to be precisified in order to make the Hauptvermutung a precise statement. What does it mean to map uniformly into M? I'll get to that in a minute. But once we have the notion of a faithful embedding, we can define what is usually understood as the Hauptvermutung in the literature, which is that if we have two faithful embeddings of a causal set into two different relativistic spacetimes at the same density, then those two spacetimes are approximately isometric above the volume scale set by the embedding density. Again, because I have quotation, that's another thing that needs to be made precise. What does it mean to say that two spacetimes are approximately isometric? Indeed, what does it mean to say that they're approximately isometric above a certain scale, a certain length scale or a certain volume scale? Okay, so now I'm going to try to talk about how these ideas have been at least suggested to be made precise and what kinds of obstacles there still are to them. I'm going to suggest some ways that might be helpful. I'm not ultimately going to be solving any problems, but I want to lay out clear, and that's my goal, what exactly the problems are. Okay, so what does it mean for an embedding to be uniform? So of course the uniformity is with respect to the volume determined by the metric. So it's usually argued on grounds of local Lorentz invariance that must mean something like uniform on average. That we should think of getting a space-time and then sprinkling points in it such that if we were to look at any bounded volume of the space-time, the probability of finding, say, n sprinkled points in that region R is going to be given by a Poisson distribution. Here, V sub R is just the volume of that region. The special thing about the Poisson distribution is that if you have disjoint regions, the distribution of points in those two disjoint regions are going to be independent of one another. Now, once again, if we think that causal sets are more fundamental, we can't really think about this directly in terms of sprinklings. Because, after all, we don't start with a relativistic spacetime. We want to somehow show that a relativistic spacetime is a good approximation to a causal set. So instead, we have to do something like statistical inference. That we have some embedding, and the embedding could have arisen with high probability from a Poisson sprinkling. So now we push back the problem a little bit from what does it mean for an embedding to be uniform to what does it mean for embedding to have arisen with high probability. This has only been suggested in footnotes in the causal set literature, but the suggestion seems to be so far that it means passing a sufficiently stringent Fisherian hypothesis test. In other words, one supposes under the hypothesis that the embedding is Poisson, and then one looks to see what is the likelihood that one would have seen the embedding that one did see if that in fact was the case. Now, there are some problems with this. So one, you might be worried about conventionality here. How stringent does the test have to be? Which test statistics do we use? It's quite feasible, in fact, that if we use two different test statistics, one test might be passed, another might not. In such a case, how do we decide whether or not that means that the embedding really is uniform or not? I think that these kinds of problems can be overcome by looking at a closer connection with observables. So it's my view that the uniformity that's required in the Hauptvermutung is really only instrumental for a kind of empirical adequacy of the continuum approximation. If we fix a set of observables that we want to be well approximated, observables that are actually on the causal set, but we want whose corresponding observables on an approximating spacetime we want to be well approximated, then those conditions of approximation should, for any given statistical test that you come up with, give you the probabilities or the stringency of that test that would need to be satisfied. So, for example, if we were able to probe with much higher energies and resolve much smaller chunks of volume, presumably the test would have to be a lot more stringent. Now, yes?
It seems that we are thinking already that space-time is one, of course, what we feel as space-time corresponds to one causal set, and not some quantum superposition of causal sets. Is that correct?
Right. So, as I said in the beginning, I'm going to be focusing on a single causal set history. And you're quite right that eventually the program would like to develop something like a sum over history approach, where each history is a classical causal set. In this respect, one might want to think of there being two kinds of approximation relations. One is a quantum version of a causal set to a classical version of a causal set, and then a correspondence with a classical causal set with a continuum spacetime. I'm just focusing on that latter relationship. You're quite right that eventually the program would like to understand better the relationship of the quantum physics there.
But perhaps there should. It's possible that the intermediate step is unwarranted. It's possible that the only connection would have to be between the quantum causal set and the classical spacetime, that you would not be able to find. Isn't it possible?
Yes, in phrasing the problem like that, you're sort of assuming that first you get rid of quantum superpositions by selecting a causal set, and then there is some approximation to a continuum spacetime, which is not at all necessarily the case.
I agree, it's not necessarily the case. However, this has been the approach that has been followed, not because that it seems unique, but it seems like the most tractable approach. Now, like Chris said, I'm not a proponent of the theory. I'm just trying to lay out the terrain. And I agree that that's one avenue that can be followed. I think the reason why it hasn't been is that there's still quite a bit of difficulties understanding what superposition of causal sets is supposed to be. And so that avenue hasn't been very much developed. But I agree with you that in principle, right, that could also be a direction to go in. Okay? So there is this open problem of how to find a viable battery of tests. Which statistical tests should we use? It's not entirely clear. And the reason why this becomes a rather acute problem is that typical statistical tests really require finite data. In this case, that would correspond to spacetimes with finite four-volume. However, that seems a rather severe restriction. And in fact, you might think, well, maybe we can partition a spacetime into equal finite volume cells and then perform tests on those equal volume cells. But it can be easily shown that the results of such tests are not going to be invariant under repartitions. In other words, whether if one tries to take this approach, it seems like the viability of understanding whether a particular embedding is uniform or not depends on an arbitrary choice of partition. This is not to say that coming up with a statistical test involving infinite data sets is impossible, but it's a very difficult task. Because in general, even extremely unlikely patterns will occur infinitely often in an infinite data set. We have to try to understand what that is supposed to mean and how we can understand a statistical inference in this context. So there's another problem which maybe alluded to before, which is that maybe requiring an embedding is a little bit too strong. That is, requiring that all of the causal relations be preserved is a bit too strong. The reason has to do with sets that have this kind of structure. So it can be shown that, for example, this kind of set can't be embedded into two-dimensional Minkowski spacetime. And indeed, there are analogs that require very few points that can't be embedded into spacetimes. Can't be embedded into the Minkowski spacetimes at least. So there's often an intuition among researchers that, in a sense, the faithfulness of an embedding should be stable in some sense. What I mean by that is that if you have some faithful embedding and you modify or add a few points to the causal set, that shouldn't significantly change the viability of it being a faithful embedding. But if we require a strict embedding, just adding a few points to a causal set that may have 10 to the 200 points in it will spoil the embedding completely. So the thought is maybe we should weaken the requirement. There are a few approaches to thinking about this, but the most common one is in terms of a coarse-graining. And this is how a coarse-graining is understood typically in the program. Intuitively, for each point, we flip a coin, a biased coin, and with probability p, we delete that point and remove the causal relations that it's involved in. So a coarse-graining, on this sense, is a causal set that could have arisen with high probability from a lattice Bernoulli process, where we go and we delete independently each point with some fixed probability p. This would then correspond to a weakening of the Hauptvermutung, where instead of trying to embed some particular causal set, we just try to look at embeddings of some coarse-grained causal set. Now, as maybe you can see, the same kinds of statistical issues are going to arise again for coarse-grainings as for uniform embeddings. And the reason, of course, is that if you have an infinite structure, what does it mean to perform a coarse-graining on a particular causal set that has infinitely many points? The result would presumably be a causal set that has infinitely many points. There's a sense in which we need to, just like before, make precise what it means to perform a statistical test on a body of data that's infinite in order to decide if it could have arisen from some probabilistic process with high probability. So I'm not going to rehearse those issues again. But there's a couple of other issues that arise from coarse-grainings. So we think that a coarse-graining should be a kind of averaging, and it's not clear that deletion should be really understood as that. If you have a lattice of atoms, for example, and you want to look at a coarse-graining of that system, as one often does in statistical mechanics, the way that one proceeds isn't by saying, let's ignore some of the atoms. Rather, one takes a kind of average of certain kinds of effects. You might use a mean field model, for example. So it's not clear that this kind of approach is actually capturing the kind of sense of coarse-graining that we actually want to. So here's another option. I haven't seen this presented in the literature, but it seems, at least in principle, viable. Instead of deleting points, we do kind of vertex identification on adjacent points in a probabilistic way. So if we have,
raise as much as you like.
So the kind of thing that I have in mind is we have 2 points like this, and we have some relations coming in here. The way that these two would get identified, you would just have a single point like this. And one can do a slightly more complicated thing to define spatially adjacent causal set points. But I won't go to, we can talk about more of the details later if we want to. I think this is probably a better sense of coarse-graining. I think probably the reason why it hasn't been used in the literature is that determining if a causal set could have arisen through such a vertex identification is computationally very, very difficult. But it's one avenue to pursue. So I also want to mention a restriction on embedding density that I think is not often articulated when people talk about the Hauptvermutung. So if the elementary volume is the inverse of the embedding density, that is the volume that we assign to a particular causal set element, so then of course graining is going to yield a causal set which has fewer elements, so we have to assign more volume to each point in order to maintain the same volume when it's embedded into a space-time. There's an intuition, however, that a sufficient decimation really makes faithful embedding quite trivial. if we decimate a causal set, if we delete enough points so that, say, each causal set gets assigned a 4 volume of something like meter to the 4th, that seems like it's cheating, right? And the suggestion I want to make, and maybe it's obvious once you put it this way, is that the maximal coarse-grained volume should be determined, again, by closer attention to observables. If we have a set of observables that we want to be well approximated, we want to make sure that the embedding density is constrained by our ability to have observables approximated in this sense. That is, observables on the causal set be well approximated by corresponding observables in the general relativistic spacetime. Okay, so here's the big one. The kinds of issues that arise here with the so the previous kinds of issues were kind of statistical in nature. I think that's kind of unusual because we normally don't think that the kinds of conceptual issues that arise in quantum gravity are statistical. The issues here are a little bit different. So how do we understand what an approximate isometry is? The original proposal for trying to understand this involves two distances. These are in quotations because they're not true distances, that are supposed to measure differences in causal and volumetric structure. So the one for the volumetric structure is rather simple and straightforward. If we pick some basis at a point, look at the determinant of the metric, and we look at the ratio here. This ratio is going to be independent of the choice of basis. It's going to give us, roughly speaking, a kind of ratio of their conformal factors, and as I mentioned before, the conformal factors associated with metric kind of encodes information about its volume. And then we look at the supremum of the natural log of this ratio over the whole space-time. The idea is that this is the maximal discrepancy in volumetric structure.
You have two metrics and two manifolds, right?
Okay, good. So one of the problems that I'm going to get to with this approach is that these two spacetimes have to be defined on the same underlying manifold, and that's how they get compared. And this is one reason why this approach isn't. People haven't been working on this approach because of that deficiency. So understanding the different causal structure, the distance for causal structure is a little bit more involved. The idea that's been proposed is to use differences in volumes of Alexandrov intervals. So here's what I mean. So we have points P and Q here. The Alexandrov interval is going to be the intersection of the causal past of P with the causal future of Q. It's just like the chronological future and past, except it also includes the boundary points. So the idea is to, if you have two metrics defined on the same space-time, look at the Alexandrov intervals for any given 2 points that are formed by those two metrics. So here we have the same diamond as before, but we might have some other space-time where the light cones are tilted this way and tilted that way. So we have a blue cone, we have a blue Alexandrov interval and a red Alexandrov interval. Their intersection is the purple region here, and their symmetric difference is the union of the red and the blue. So the idea is, one way to compare causal structure is let's look at the ratio of the volume of the symmetric difference. Volume has to be taken with respect to one of the two metrics, of course, to the volume of the union of the two, and the whole thing. So this is what they do. They define this function. Here we have that ratio that I was just mentioning of the volumes of the symmetric difference to the union, and then one just looks at the supremum of this. However, one imposes a restriction, and this is how they get at the idea of structure above a certain scale. One only looks at unions of Alexandrov intervals that have a volume that is greater than some elementary volume that you decide on. So here, L is the elementary, say, Planck length, and L to the D, where D is the dimension of the space-time, is the elementary volume. So one of the problems with the proposal is that there are a lot of technical problems with it. It ends up making too fine distinctions between causal structures. So one aspect is that if you take Minkowski spacetime and you look at a compact, non-conformal perturbation of that spacetime, it's always going to be at a maximal distance from Minkowski spacetime once you make for an appropriate choice. And a lot of people see that as not being very satisfactory. It makes too fine distinctions between causal structure. So there has been some work to propose a corrective to this problem, but it introduces a host of other problems, and so it doesn't seem to have gone anywhere. I'm not going to talk about those. But like we just talked about, the whole scheme is restricted to spacetimes that are defined on the same underlying manifold. Now, causal set theorists are interested in part on capturing a notion of scale-dependent topology. There is a very strong intuition that many researchers have that if we were to zoom in on the structure of space-time at first, it would look relatively anodyne, and then as we zoom in, it gets more complicated, and once we get into a small enough scale, we have a very complicated topology corresponding to all kinds of quantum fluctuations. Now, part of the problem, of course, primarily is trying to make precise what that intuition is supposed to be. The hope for causal set theorists is that we can capture this by looking at differences between spacetimes relative to certain volume scales. But if we want to capture that, we need to be flexible with the underlying topology of the spacetimes that we want to compare. So even though this was the initial proposal, it seems that most theorists have abandoned it. I think that there are interesting reasons to consider it, external reasons to consider various versions of it that are kind of external for considerations of quantum gravity. In general, it's often an interesting question to consider what does it mean for two spacetimes to be similar, and this is one possible way of capturing it. But it seems that this particular way has been abandoned. There's another proposal, a statistical proposal that's kind of very, very clever and well adapted to the causal set program. The idea is let's sample endpoints at random from a spacetime and consider the induced causal structure. So one can write down an expression for the probability that drawing n such points from an isometry class, G, will yield a particular causal set, right? So remember, causal set is just a set of points with its causal relations. Here, the causal relations are induced from the underlying spacetime. So the idea then is then we can compare isometry classes, G's, according to their profiles of these probabilities for all causal sets that have the same underlying cardinality, where n, the underlying cardinality, is going to be defined by the embedding density. So one proposal that Bombelli made is that we can, since the sum of the probabilities of drawing a particular causal set from an isometry class, summed overall possibilities is equal to 1, we can think of the square root of these quantities as a coordinate, say, a particular point on a high-dimensional sphere. And so then we can measure the difference between two isometry classes just by looking at the angle that's subtended by the two rays on the unit sphere. I think this is neat and clever. One might have a couple of worries about it, though. So there are many inequivalent ways to encode differences in these probability profiles with a distance function. Why is thinking about it in terms of the angle subtended on this high-dimensional sphere the right way to go? I think this problem is not as important because of the same reasons that we can apply considerations of observables to determine what the relevant notions of approximation need to be. So you can come up with a range of different distances. For any distance you give, we just need to figure out the minimal distance, say, that two isometry classes need to be within in order to have the observables we want to be well approximated to some given error, be well approximated to within that given error. There are other problems, though. So it's very difficult to calculate for large n. As a practical problem, there's a deeper conceptual problem, though, is that it only works for spacetimes of finite volume. Remember that If you have a finite volume, then if you have some embedding density, then the number of points on average that you are going to want to embed into a space-time is going to be finite. However, if the volume is infinite, then no matter which embedding density you choose, you're going to have an infinite number of points. The total number of different causal sets that you could have gotten by sprinkling points into a space-time with infinite volume is infinite, and so the probability that any particular causal set will arise is going to be 0. There doesn't seem to be any suggestions in the literature for how to get around this problem, which is another reason why there hasn't been a lot of progress on this particular proposal either. Yes?
Yeah, isn't this a problem only under the assumption we were discussing earlier, that to a given causal set there should correspond a given space-time? The fact that the probability for any given causal set to be a given space-time is 0 is only a problem if you want a one-to-one map. If you only want to have an average correspondence, then maybe it's not an issue.
Yeah, I agree that if one can develop a way of understanding that correspondence, then you might be able to avoid this problem. The Hauptvermutung, as is usually understood, though, is not about the relationship with a quantum causal set and a space-time, but with a classical causal set or a causal set history.
I mean, what is exactly statistically here? I mean, you can imagine, having hydrodynamic coming out of the statistical mechanics of particles. Everything is classical, but it's not that there is a one-to-one correspondence between a given configuration of particles and a given configuration of the corresponding fluid.
Oh,
it's not an issue of quantum versus classical, just a matter of...
So here, one is not right. The correspondence here is not a one-to-one correspondence between causal sets and space-times. It's saying that if it's a little bit more complicated, right? Is that if we can take a causal set, maybe it's suitably coarse-grained, and embed it into two different space-times. Not that those two different space-times are identical, but they're almost identical up to structure that is above a certain scale. So the corresponding thing would be that if we have an underlying statistic, okay, yeah, right, yeah. So in part of the difficulty is making precise exactly what that is supposed to mean. And there's a lot of different proposals on this last part, and we're going to get to the last one right now, in fact. And this last one is actually quite different from the first two. It takes its cue from fairly recent, at least since the 1980s, results in metric geometry. So there's this concept called the Hausdorff distance. It's been around, obviously, a long time, if it's named after Hausdorff. But the developments start with this. So you can think that this is a technical definition, but there's a very intuitive sense for what the Hausdorff distance is. So consider some metric space, right? Forget about space-time. We just have some metric space. We have two compact subsets of the metric space, x and y. The Hausdorff distance between them is the largest distance that you would have to travel if an adversary set you on one point of one of the two sets and you had to walk from one to the other. So in this particular case, it's going to be the maximum of these two differences, because if you were to be set on this blue set here, this is the maximal distance that you'd have to walk. If you were set on the green one, that distance up there is the maximum one that you would have to walk. It's a way of measuring, in a certain sense, how close two compact subsets of a metric space are to one another. So Gromov in the 1980s proposed the following idea. We can define now the distance not between two compact subsets of a metric space, but two metric spaces, as by looking at the infimum of the Hausdorff distances of those two metric spaces when they're embedded isometrically into a common metric space. The idea is we have our two metric spaces, we have some bigger space, we can embed them in a lot of different ways, but the Gromov-Hausdorff distance is the distance that corresponds to the best match between the two, the minimal Hausdorff distance between the two sets. One of the reasons why this is so fruitful is that Riemannian manifolds are metric spaces, vis-a-vis the geodesic distance that's induced on them. So with this distance, one can develop a convergence theory, For example, for what it means to say that, say, you have a sphere and it's collapsing to a pancake, you can make precise exactly what it means for a sphere to collapse into a pancake, a flat pancake, and arbitrarily high dimensional analogs and much more complicated shapes. And the idea is, this is very interesting because it doesn't depend so much on matching of the underlying details of the manifold, like the first proposal. It doesn't assume necessarily that the structures have a certain volume structure, like Bombelli's proposal. So the thought is, can we extend this to the Lorentzian case?
Excuse me, you are saying X and Y are compact here.
Yeah,
right?
yeah. That's a good.
Okay.
This is an important point. I'm going to get to that in a little bit. The reason why it's usually assumed that X and Y are compact is that you can have situations where if they're not compact, the distance is going to be infinite, and then you don't get a good convergence theory in that case. This shows up later on. So the thought is that we look at not a metric space, but something called a Lorentz space. It's a space with a Lorentz distance function. And the properties of it correspond to the properties that we think correspond to the future-directed geodesic distance in a space-time. So, for example, the geodesic distance between 2 points is going to be 0 if they're the same. If there's a future-directed curve from one point to another, then there isn't going to be a curve from the second point back to the first, right? We're assuming here that we are in distinguishing spacetimes that don't have any closed time-like curves. And also we have the reverse triangle inequality, which is familiar for Lorentz distances. So the idea is maybe we can develop a convergence theory in the same way for Lorentz spaces instead of for metric spaces. So the thought is that we can consider two. So we consider two spacetimes to be approximating one another. When we have a map, when we have a pair of maps, such that when we map one into the other, the Lorentz distances between points are well approximated, and we have a map from the other into the one, in which the Lorentz distances are well approximated. And then we say that it's epsilon approximation of the two. So Noldus then proposed that we look at the infimum of all epsilon approximations in this sense. Now, I think it's a very interesting approach. The relationship with observables has not been worked out in detail. One version is in fact restricted to compact, globally hyperbolic spacetimes. Now, what this means in particular is that the spacetimes are going to have boundaries, which is a problem if you want to do this kind of approach with cosmology, in which you don't think necessarily that you're going to have time-like or space-like boundaries. Another very recent version relaxes this a bit, but it introduces some technical conditions whose interpretation is not clear. In that the authors explicitly say they're not sure how to interpret the technical conditions. The exciting thing about this is that if one can make causal sets as well into Lorentz spaces, then there's the possibility one could compare causal sets in spacetimes directly without the intermediary of a faithful embedding. One just looks at the Lorentzian Gromov-Hausdorff distance between a causal set and a spacetime instead of having to worry about all the statistical details of an embedding. But this approach is very new, and there is exactly one archive paper on it. So it remains to be seen how it gets developed. So there's a lot of obstacles and forks in the road ahead. And I suggested that, at least on the traditional approach to the Hauptvermutung, that some problems can be mollified by a closer attention to the approximation of observables. I haven't argued for this explicitly, but by laying out the details, it seems to me that if a sufficiently precise version of it were true, it doesn't seem to envision any kind of derivation of general relativity from causal set theory. Yet, nevertheless, its fulfillment would seem to provide some kind of explanation for the success of continuum spacetime. That's it. Thank you.
took some questions from the floor, and we're running a bit late, but I think maybe one question, and Jeremy's quick off the mark there.
Well, thank you for explaining. Lots to ask about, but
Yeah.
one thing that it reminded me of is this other line, namely the Penrose line,
Yeah.
about state reduction being induced by when the gravitational self-energy of the difference of the mass configurations reaches a certain threshold. Probably these people don't relate to one another very closely, but shouldn't each one be looking at the measures worked on by the other? Because although you've worked with M, G, it's an equally natural thought that actually one could think about big T.
Absolutely. Part of the difficulty, though, is in principle, we want to be able to say something about matter fields on causal sets. One of the difficulties is giving discrete analogs to propagation of matter fields. And people are still working on that subject and it's still an active topic of research. So I imagine that if they did talk with one another, they might very well find some points of commonality and fruitfulness. But as far as I know, that they haven't.
Okay, well thanks. Again, I think we should move on to Maria's talk.
Yeah.
Thank you very much.